Well, thank you very much, Susan, and thank you all for joining us today. Today, the subject for our webinar, as you know, is large steam boilers, but like all of our public webinars, it's our intent to inform and not to try to sell or influence in a biased way. As a matter of fact, we acknowledge the point that we have very reputable and capable competitors out there who, like ourselves, have excellent products covering a wide range of applications. We also understand that large capital projects of this type are won by the company who consistently delivers not only a quality product, but goes the distance to truly understand the customer's needs and then delivers the right product containing the best cost-value relationship, and that would be time after time. So that said, the more informed the buyer or the specifier is in his or her understanding of the large boiler market and its offerings, the more insightful they become, and thereby increasing the chance the project will be successful all the way from project specification through order placement and then final installation and commissioning. So my intent today is not to cover the entire waterfront in this short period of time, but rather to apprise you of some of the important aspects of the market, what the market is demanding, some demand satisfying product examples, and then how these products are designed, and then finally, where they are often applied. In other words, what industries would we find them? Now, I'd like to begin by clarifying a question we often receive from customers and engineers, and that is, why would I choose a water tube boiler over a fire tube? Now, if you take a look at the slide that's before you right now, and the fire tube boiler here on the left, a water tube boiler, when we're comparing pound of steam per pound of steam, apples with apples, the water tube boiler is going to be more expensive, anywhere from 25 to 40% more than the equivalently sized fire tube. And that's because these boilers, the way they're constructed, the materials used, are really more expensive. They just are. And then depending upon the diameter break of the fire tube, these become very, very competitively priced, and that's why I'm giving you a range 25 to 40%. The other thing is a water tube boiler, just the way it is constructed, is a lot more labor intensive. So therefore, lower price for the fire tube is definitely an advantage for it. A fire tube boiler also is going to be more efficient. You don't have as much heating surface, square feet of heating surface, in these water tube boilers, and there's a good reason for that, and we're going to be getting into that as we go through this presentation. In order for it to equal the efficiency of a fire tube boiler, size for size again, we're going to have to add an economizer, and that, of course, will add to the overall cost of the unit, therefore giving us the disparity in price between fire tube and water tube, or adding to it. A fire tube boiler is going to be a little easier to clean. You can just see by the way a water tube is constructed, to be able to inspect and clean these tubes can be somewhat difficult. That's why water quality becomes extremely important. The type of feed water that we put in these boilers becomes critical, and we'll talk about that as well. So a fire tube is going to be a bit more forgiving. And then a lower headroom for a fire tube than a water tube. It's higher. So headroom becomes a consideration. The point, though, is we've got larger capacities with a water tube boiler. We're talking about sizes that range from 10,000 pounds per hour up to what we'll be speaking of today, packaged boilers, whether they be a completely packaged unit or whether they be modules that are shippable and then completed in the field. We're looking at sizes up to 650,000 pounds per hour. Now, your fire tube is going to be limited to horsepower, about 2,500 horsepower as a package. Now that's about 86,000 pounds. So that's where the fire tube is going to top out, about 86,000 pounds of steam per hour, whereas these will take you to 650,000 pounds of steam per hour, about 19,000 horsepower as opposed to 2,500. Also, the fire tube boiler is going to be limited when it comes to overall design pressure, the pressure at which you will be able to operate that boiler. These you can take the water tube up to 900 pounds very easily, and in special occasions, special designs, up to 1,500 pound saturated steam pressure. So when we get into very extreme horsepowers, we get into large capacity loads, we get into large design pressure requirements, that is where the water tube boiler is going to be essentially your only choice. We can also integrate a superheater with a water tube boiler. Can't do it with a fire tube. It has higher steam quality. So steam quality, the amount of moisture in the steam itself, is critical. Your water tube boiler is going to have an advantage, a distinct advantage. And of course, lower motor horsepower. I'm talking now about the fan motor. We don't have as much pressure drop through a water tube, size for size, as we do a fire tube. What you're looking at here is 4 passes of resistance that we have to overcome. So it really depends upon the particular application, whether we choose a fire tube or a water tube. But when you get to certain capacities, over 2,500 horsepower, your only choice is a water tube. Or if we get to large design pressures and operating pressures as a result, it may be the water tube's the only real advantage here, or the only choice that you would have. Now, when we look at water tube boilers as a group of product, they start out very small. It's a wide range. Here you're looking at an O-type water tube drum-type boiler, membrane design. This particular one is 150 horsepower. That's about 5,000 pounds of steam. Here's another O-type water tube boiler, but it doesn't have vertical tubes. It's got serpentine tubes. It's what we call a flex tube. So this is available for hot water or steam, lower high pressure steam, sizes up to about 500 horsepower. What you're looking at here, though, is a 300 horsepower boiler, about 10,000 pounds of steam per hour. So we start out small, but then get very large. And we start looking at different types of water tube boilers. And what you're looking at on the screen right now, these are packages. All right, they will ship to the job exactly as you see them, with a burner, casing, and so on. Everything is complete. This is an A-type. It's got an upper drum or a steam drum and 2 lower mud drums. We have an O-type configuration with a steam drum and lower drum, very symmetrical in design. This was primarily used for rental type boilers that would go on trailers. If you have a D-type, as you see here, it has a very high center of gravity. These are very low center of gravity, so it ships very well on a truck and very, very good for rental type applications, the O-type. And then, of course, the D gets its name because it looks like a D, and it could be either a left-hand or a right-hand burner configuration. This is a left-hand burner. So you've got your upper drum and lower drum, and then your furnace is over here. So the D-type, the A, and the O-type configuration. And these are all packages and can ship either this way or as modules, and I'll show you that just a little bit later. Let's see, I missed a slide here, I think. Oh, here we go. Now, when we look at water tube boilers, these are what we call industrial water tubes or drum-type boilers. What you see down here is a generator, at least what I used to call, in the early days, at least when I started here at Cleaver-Brooks, we called these steam generators. They're also called forced circulation type boilers. What you see here, it happens to be an O-type, but it's a drum-type boiler, and it relies on natural circulation. It's the pressure density differential between the upper and lower drums that gives us that circulation. So as we begin to transfer the heat in the furnace, and we start to generate steam, we have nucleate boiling going on in these tubes, and then it releases up here in the upper drum, but it's all done naturally. The saturated water then below the steam line, if you will, the steam accumulation area in the upper drum, finds its way through these downcomers, and we start to recirculate. So it's all natural circulation. The steam generator that you see here requires a pump. What you have is about, well, let's say 80% steam in these tubes versus 20% water. Just the opposite in a water tube boiler. The ratio of steam to water is water much higher, 80% water as opposed to 20% steam. That's how we get that natural thermal circulation. These steam generators are good boilers. They've got good applications, but what we're concerned about with those is what we call high temperature flux, heat flux, which is the temperature differences or temperature gradients that can occur because we have so much steam. So we've got to be careful with these boilers that we have very, very high water quality, or we can have some problems. They're quick steamers. They do an excellent job from that perspective, but we've got to watch the water quality. As far as the market is concerned, and we've been in this market along with our competitors for many, many years, Cleaver-Brooks for over 80 years, and we've gone out and talked to our customers and looked at applications. And when you're talking about industrial water tube boilers, many of these units that we build are custom made. We have to look very closely at that system, what its requirements are, both as far as fire side and water side, okay? The steam requirements as well as the, let's say, the emission requirements, what the turn down has to be. It gets very, very complicated, or can, because these jobs are so large in terms of steam capacity. So our customers have been telling us all along what we need. We definitely have to have fuel efficiency because of the inordinate amount of fuel that these boilers are consuming. If we can save 1 or 2 or 3% in fuel, we're not talking about chump change here. We're talking large, major dollars. Low emissions, of course. This is something that we are becoming much more cognizant of as a nation, as a world, in terms of polluting, the pollutions that come out of stacks. And the ones that are being looked at most closely, of course, it starts with the mobile sources with our cars, but then it goes quickly to utilities and these large megawatt generators and large, huge industrial water tube boilers that we'll be talking about today that emit a lot of effluent out of that stack. We've got to look at these emissions and make sure that we not only conserve the carbon footprint by burning less fuel, but then what's coming out of the stack has to be also very closely looked at so that we don't pollute the air, cause ozone, and have other problems in terms of carbon monoxide and so on, particulate. And then, of course, they're saying we want a high value to cost relationship. It's not just the boiler cost, it's what do we as an industry deliver along with that boiler? What kind of technical expertise do we bring to the job? How can we best serve that customer in attaining his needs? And then they want integrated controls, and we'll get into that. Reliability, of course, is key, making sure that these boilers stay online regularly. We don't want outages. We want to make sure that we can anticipate problems before they occur. That gets into the integrated controls, ties into reliability. Low maintenance. What can we do to lower the cost of maintenance, lower the downtime? And of course, single source responsibility. And that just ties into getting rid of the finger pointing, right? Oh, it's the burner guy's problem. Oh, it's the control guy's problem. Oh, it's the boiler guy's problem. No. One person, single source responsibility, bring it all together, be accountable. So it's a tall order. What about the market? Over 200,000 pounds. Well, you can see here the number of projects and how they have been increasing over the years. I'm starting out here at 2005, and you see 2012 this year projected. And we've gone from a nominal number of packaged units way back here in 2005, and all of a sudden increasing rapidly. And what's driving that is there's an aging population of large industrial boilers out there. A lot of these are coal-fired, so they're concerned about the emissions as well. They're also looking at ways of maybe burning other sustainable fuels like biofuels. And now, because natural gas is becoming more and more prevalent, if you will, more and more available, we've got a lot more of it, especially with the fracking processes that we're going through today. And it's getting cheaper. So we've got a lot of customers saying, look, I think it's time to bite the bullet. We'll tear this old boiler out, put a new one in, or we'll retrofit and take this old boiler that I have and bring it up to today's standards. So it's about a $200 million market today, over 200,000 pounds per hour. That's about what it is today. And what's driving it, of course, is old boilers, the need for higher efficiencies, and then, of course, the call for lower emissions. Now, when we look at the way that our industry is addressing these needs, what I'm talking about today primarily are going to be packaged units. So we've got a fully assembled one-piece package, which I showed you originally when I showed you the A, the D, and the O type boilers. We also have partially shop-assembled two-piece designs, which I'll show you. Then we have modularized three-piece designs as you get into larger capacity needs. And then we have the field-directed. So if we just, for today's discussion and for our focus, we're looking at 200,000 pounds per hour up to 650,000 that can be built or delivered in these forms. Now, how does it break out? Well, if we look at one-piece, fully assembled units, 10,000 to 300,000 pounds of steam per hour, we can ship those as a complete unit in one piece, and I'll show you some examples of that. As we get into some larger capacities, 300,000 to 500,000 pounds per hour, we'll go to the two-piece. We're calling an elevated drum, two-piece, and I'll show you how that works. And larger sizes, packages, modularized packages from 500 to 650,000 pounds of steam per hour, that's 19,000 horsepower, come in three pieces. And then, of course, there's the old reliable field-directed unit. Now, I will say that these modules can get a little expensive when it comes to shipping. And in some cases, maybe the only answer that our customer might have, if we're going to be truthful with him and honest with him or her, would be a field direct. Maybe it's got to be stick built, as we say. It has its place, but our customers are saying single source responsibility, let's mitigate the field time, and if you can make these boilers, either modules or packages, more convenient and less expensive for me to install and operate overall, that's the way I'll go. But we also have to look at the field directed as an option. Now, here's a package boiler, 300,000 pound per hour. Now, normally when these boilers get over 225,000 pounds per hour, we can't ship them as a complete unit. We've got to ship the burner and controls loose, and that's what you're seeing right here. You can see it on the truck. This truck, by the way, has 74 tires if you were to count them. But it's complete. That will arrive at the job site complete with the boiler, the pressure vessel, the casing, the burner, the controls, all done. Now here's a couple 100,000 pound per hour boilers. This on a rail car and this one on a truck. But these are the complete packages. Now here's a 50,000 pound per hour boiler, and what I wanted to call your attention to here is the single source responsibility, the total integration is reflected here in this picture. Now it looks somewhat complicated, but really it isn't. It's a D-type boiler, 50,000 pound per hour as you can see. We've got our fuel line all pre-piped and wired. Our pilot line coming in here. We've got standby oil. This is our oil line coming in when we go and burn number 2 or number 4, number 6, whatever it might be, oil. We also have our secondary air fan for combustion. That's all completely packaged, wired, and mounted. This is your flue gas or your secondary air inlet for combustion. This is the connection for flue gas recirculation. So in this particular case, we had to lower the NOx. We had a low NOx burner on here, but we also had to introduce flue gas recirculation to lower the NOx even more, to take it down to, let's say, 20 parts per million from a normal 120. So we had to use some of the flue gas coming out of the stack, ducted into the secondary air supply, and bring it into the burner for combustion to lower the, what we call thermal NOx. That's called flue gas recirculation. But again, when you see these packages, whether they come from us or one of our competitors, this is our way of addressing the single source responsibility. This is our way of addressing the cost-value relationship. We're trying to cut cost out of the total project and give our customers as efficient and reliable a package as we possibly can. Now, looking at this, you see 3 units. These are packaged boilers now that shipped on a truck minus the burner, because in this particular case, even though it's 220,000 pounds, and I said before, at 225,000 pounds, we have to ship the burner loose. We had to ship it loose here because this unit included a superheater. And it's a convective superheater, so it took up some space in that convection area. And so in order for us to be able to deliver the capacity that we needed, we had to extend the length of the boiler a bit, which meant that for us to ship it, we had to take the burner off. But once mounted here in the field, we're looking at a complete package. Now, it took us about, in an ideal situation, where we haven't got conflict with other disciplines on the job and so on, it takes about 25 man days to mount that burner and all the controls and wire it on this boiler. About 25 man days. Now, we're going to move from the packaged water tube boiler to the what we call elevated drum or 2-piece and 3-piece modules. In this particular case, I'm showing you a D-type design configuration. You can see that we have the elevated drum, and we also have that drum which is connected to the lower drum through what we're calling the downcomer. Here we have the generating section of the furnace side. These tubes are generating steam into this header up into the steam drum. Now, these range anywhere from this capacity 300,000 to 650,000 pounds per hour. Now, a 650,000 pound per hour boiler is going to have a burner on it, or total of burners, total input I should say, of about 780 million BTUs. So if I'm looking at this particular boiler right here, which is 650,000 pounds per hour, we have 4 burners, each of which is rated at about 195 million BTUs per hour. Now you know why we have to pay so much attention to efficiency, right? We're burning an awful lot of gas here. The thing about these elevated drum designs, the other advantage that it gives us, is the fact that we can make this drum as large as we want, plus it does not encroach on either the convective side or the radiant side of our boiler, which means that we can increase the size of that furnace to lower the heat release rate down to areas in the 60 to 70,000 BTU per cubic foot of furnace volume. Also looking at that heating surface, that's about 47 to 50,000 BTU per square foot. Well, now why is that important? Well, it's important from a couple of standpoints, not the least of which is the feed water that comes into this boiler. If I can lower the absorption rate in that furnace, I don't have the rapid heat flux as I might have in a steam generator. So it lowers that. It mitigates that to a large extent. I'm not getting those temperature transients that I would in other types of boilers that have a higher heat release. It helps me there. It also helps me from the emission perspective in that I can control the temperature of that flame more readily to lower the NOx requirement. The other thing, of course, with these are these downcomers, which are isolated. So it gives me rapid circulation through these generating tubes as they generate steam and water into this upper drum to be separated, which I'll show you as well. Now, looking at the elevated drum design, here's this D-style 225,000 pound per hour package boiler. They get larger as you go along. Here's a 300,000 pound per hour boiler that requires 2 burners. And then, of course, the D-type right here at 500,000. All I'm trying to show you with this is how this boiler is getting so much taller, but not that much wider. The other thing is that with these large steam drums, I've got more steam accumulation area. So when I've got a sudden surge or a need for steam, I've got more accumulation in this upper drum than I would otherwise, because with this modular design, I can make it bigger. And also, I've got a larger margin of water before, the water right here, anywhere from about a third of this drum is water. Before this evaporates all the way down in a low water condition, I've got about 5 minutes between proper level and the low water condition. And we certainly don't want to have a waterside occurrence here with these boilers. No boiler for that matter. Even a 30-gallon water heater is devastating. Here you see the 425,000 pound per hour elevated drum water tube boiler. You'll notice that it's kind of hard to see, I think, with this picture, but these tubes are all membraned. Okay, they're attached to the drum, or to the manifold, I should say. In this particular case, our steam drum is going to be a separate piece that'll be mounted in the field. But they're all membrane tubes. This eliminates a lot of the refractory that you'll find in some of the older designs. Gets back to what our customers are saying. Let's lower that maintenance requirement. Now here's a 300,000 pound per hour unit which is being shipped. It's an elevated drum boiler. And you can see that just the size difference right here between it and a standard size packaged water tube boiler. This is 300,000 pound per hour. It's got superheat, and that, therefore, like I showed you in that picture before, is going to extend the overall length of that unit because of the superheat. Now this gives you a good shot over here of what that elevated drum boiler looks like, whether it be a single, a two-piece or a three-piece. You can see here the upper steam drum. These are the downcomers. We need that pressure density differential to give us that good circulation. These isolated downcomers help that considerably. Then, of course, you've got your generating section here. And this is your flue gas outlet. Now, this particular one is a 500,000 pound per hour elevated drum water tube boiler. It's about 600 million BTU input. So each one of these burners is about 300 million BTU. Now here you see a utility application where we have 5 426,000 pound per hour boilers equating to 2.1 million pounds per hour. You only see 3 of them, but there are actually 5 on the job. Now, these are economizers that you see on the side of the boiler. Because this is a utility application, these boilers are generating steam for steam turbines that are driving generators. Anytime you get into the application of steam being used with turbines, we have to be extremely concerned about water quality. Now, This is the upper drum. It's kind of a standard design that you see right here. The upper drum or the steam drum in a water tube boiler. This pipe right here is your feed water pipe. This is your chemical dispersion tube right here. Now, what you also have is a chevron separator right here below the steam nozzle itself. There's also some other baffles, which I'll show you next, that are right in front of the steam generating tubes. The whole idea here is to separate the steam as effectively as we possibly can from the saturated water. That's what we call water quality, okay, or steam quality, I should say. Not water quality, but steam quality. How much moisture is in that steam when it goes out the nozzle into my system? With a fire tube boiler, you're talking about 98.5% pure. In other words, it's got about 1.5% moisture in your fire tube boilers. Those have to have steam separators in the steam line to be able to improve the overall quality of the water, or of the steam, to remove the moisture. Water tube boilers are set up normally to achieve 99.5% moisture, okay, or quality, giving us only 0.5% moisture. Now we can put additional separating devices in this drum and take us down to 0.5%. And that's what you'll see here, a chevron separator. You've got your baffles here, which are now in front of your generating tubes. The whole idea is for this steam to take a very circuitous route through the cartoning, through these separators, so that what comes out can be as low as only 0.1% moisture. And that could be critical for those applications, especially turbines, that cannot tolerate any moisture in that steam. Now, what you'll also find in what I showed you before are superheaters. Well, what are superheaters? Well, superheaters take that saturated steam when it comes out of the nozzle, and it heats it further. It adds additional sensible energy to it. In other words, I've got 600-pound steam here, which is equivalent to 485 degrees Fahrenheit. But what I want to do is I want to raise the temperature of that steam and still stay at about 600 pounds. I add superheat. So what I'm doing is I'm adding sensible energy. So now my 485 degree steam has been boosted to 785 degrees. Now remember, the critical point of water, where it becomes nothing but a working mass of steam, if you will, no further evaporation because all the moisture is gone, is 705 degrees and equivalent to 3,200 pounds. Here I have 785 degree steam, but only about 600 pounds. That's superheat. Sensible energy added to that heat, added to that steam. So what you're looking at here is what we call a convection superheater. It's in the convection side of my boiler. This is my furnace. Here's the convection. So my superheater is taking steam from the upper drum, bringing it in, taking it through a series of baffles and headers, and heating it up further and discharging here. Looking at it from a plan view, here's my furnace. I've got vestibule tubes here in the back where those hot gases exit, come across the superheater, add that sensible energy before it goes up and out the stack. And in this particular case, it was going to an economizer. Now here's an A-type boiler with a convective superheater system. And because we bifurcate, or as we drive our flue gas down the center of an A boiler, that gas divides and goes equally either side of the boiler through the convection side, or through the convection sections. That's why I've got two superheaters here. So remember, all the saturated steam coming out of this boiler is being superheated in this case. Now here is what we call a radiant type superheater. These are good from the standpoint of footprint. I can put all of my output from this boiler through this radiant superheater and put it in my furnace, mount it in the furnace. I can reduce the amount of heating surface that way, and therefore the overall footprint of the boiler stays smaller. This is also good from the standpoint of consistency. In other words, even when this burner cycles off, you've got a lot of residual energy in that furnace, so I'm still applying heat to the radiant superheater. The problem with these, though, is that you really have to watch your water quality. You have to really watch flame impingement. So when radiant superheaters are applied to a boiler because of footprint, we've got to make sure that the proper engineering goes in to assure ourselves that we do not have problems with this radiant superheater because it's in such a hot area, if you will. The radiant area of that furnace is extremely hot. We're looking at temperatures in excess of 2,000 degrees here. So you have to be very careful of flame shape and size and length so that we don't have problems with that superheater. And the water quality as well. Now, there are some applications where they just want a small amount of superheat. And quite frankly, it doesn't make any sense to try to incorporate that small superheater in a boiler. First of all, it just wouldn't work anyway. You've got to, how would you protect it? How would you control the flow? So we can go to external superheaters. Why would I need something like that? Well, maybe what's happened here in this particular case is I've got a process that's been added on, and I've got hundreds of linear feet of piping from my power source, my boiler, to that particular process application. And I want just a certain amount of superheat to be applied. Maybe it's only 20 degrees, or maybe it's 50 degrees or 100 degrees of superheat to be applied so that that steam does not condense before it gets to the process. That's the only reason I'm adding that superheat. It's that sensible energy. So it won't condense by the time it gets, or before it gets to the user. So we can use external superheaters. There are some applications that we as an industry run into where that would be our recommendation. Now, water quality, of course, is extremely important with these water tube boilers. As I said before, even if we're doing elevated drum design where we've got lower heat releases in the furnace, it's still very important with these boilers that we watch the water quality because the overall heating surface in these units is relatively small compared to a fire tube, for instance, which would be a little bit more forgiving. So we have to look at the water that's going into the boiler as well as the boiler water itself. And the main thing that we're concerned about, of course, besides iron and copper and other things that we have to be mindful of as far as the feed water before it goes into the boiler, but the hardness is so important. You can see as I increase in pressure from 300 to 450 to 600, it becomes a bit more punitive. We've got to watch it. The higher the pressure, of course, the commensurate temperature is going to increase as well. And the higher that temperature, it's a lot easier for these rocks to drop out of the water, and I'm talking calcium and magnesium. So we're looking at three-tenths of a part per million. 3/10 here, 2/10 here. Remember, looking down here, 1 grain of hardness is equivalent to 17.1 parts. Very important that we have good either warm lime or it could be zeolite water softening. Extremely important. The other thing is the boiler water itself. We've got to watch the alkalinity. And you can see what happens with the alkalinity tolerances as we increase in pressure. Also, the conductance, all right? What's the TDS? What's my conductivity in these boilers, which is measured in micromoles? You can see the tolerances here, and as I increase in pressure, they become more stringent. And then the overall TDS, 0.2 to 1. We have to really control that, and of course, that's a continuous blowdown. The more TDS we have, the more we have to blow it down to stay within these tolerances, and of course, that effluent can be reclaimed through a continuous blowdown separator, let's say it could be a flash steam recuperator, or it could be a blowdown separator and recovery unit. We've addressed what I was going to address anyway as far as the pressure vessel, the boiler is concerned. Now let's spend a few minutes on the burner. Here you see a 600 million BTU per hour input burner combination. Now this particular one is low NOx, about 9 parts per million, and that 600 million then input would be affixed to a boiler that generates about 500,000 pounds of steam per hour. What's very important with these burners is that they are properly matched to the furnace. This is where that total responsibility, total accountability of the manufacturer comes into play. We have to make sure that these burners are properly sized and configured for this particular furnace. Because the last thing in the world we want is impingement. The last thing in the world we want is generating CO because of incomplete combustion. The last thing in the world that we want is low efficiency, low combustion efficiency. This is the radiant area. Remember, when we get into emissive absorption in this area, we are talking about delta T differences that are at the power of 4. High energy here that we have to recoup. That's why these furnaces are as large as they are. A lot of BTUs to be grabbed here. We're looking at high Reynolds values, and we're also looking at optimizing the overall heat transfer with those high Reynolds numbers. We do this through computational fluid dynamics, wherein these high temperature Reynolds values are associated both with inertial and viscous forces. In other words, we have to make sure that we're breaking up that laminar flow, getting that good heat transfer. And we're looking at values in excess of 4,000 with our Reynolds numbers. So we can compute what is going on with these furnaces, the burner furnace matching, by using computational fluid dynamics. It not only calculates, but also shows us visually what's going on with that particular match. And then we prove it through what we call finite element analysis, which reduces the complex partial differential equations to smaller, less complex linear equations. And then through the use of matrix algebra, the CFD, or the computational fluid dynamic model, is either proven or then adjusted. So in the end, what you wind up with is a burner configuration that has been now designed and configured for that particular package, giving us the type of airflow, the type of shaping, the length, the amount of emissivity in the furnace that we need, the high Reynolds numbers. That is all now been completed through the computational fluid dynamics, and the burner is then matched to the burner. The burner is then matched to the furnace. Now, when we get into the reduction of NOx, I had mentioned earlier on the use of flue gas recirculation. There are certain customers out there that require NOx to be lowered to the point of very, very low single digits. Maybe I'm talking 1 or 2 parts per million. In these particular cases, in addition to flue gas recirculation, I may be adding a selective catalytic reduction system that you see here, where we have ammonia as the reductant, and then across a catalyst, it's laid on a catalyst, the flue gas passes over it after it's come out, after flue gas recirculation is part of the combustion process now. So we've lowered our NOx to a certain level. It comes into the SCR, and we come out at there's very, very low levels with nitrogen and water. Selective catalytic reduction. As far as the overall controls for these boilers, we have a burner management system, and we also have a combustion control system. And the combustion control system, it's essentially ancillary inputs which monitor and control the overall operation based on ever-changing variables such as steam flow, feed water flow, drum level, ambient air draft, you name it. So I've got burner management, which is sequencing and controlling my burner, integrated with a combustion control system that is now tying in all those other variables and monitoring and controlling those as well. It's all then packaged in a complete control system, PLC-based today. Most of these jobs are customed. So I've got my burner management system, I've got my combustion control system, all integrated and wired into either multiple panels or a single panel as it arrives at the job site. It might also include things like fully metered cross-limited control systems where I can linearize and measure process variables such as pressure, fuel flow, and airflow. A fully metered cross-limited system like this, what it's doing for you is it's assuring you that no matter where I modulate, air will always lead fuel. In other words, I want to stay on the lean end. I never want to go fuel rich or have a combustion occurrence, especially with the inputs we're talking about with these boilers. And then, of course, for the operators, the PLCs today have very, very user-friendly graphics, touch screens, switches, alarms, everything there to be able to not only show them what's going on operationally now, but also a lot of information that can be logged, can be trended, can be sent to the facility itself, to various locations, or remotely. And then as far as maintenance is concerned, we've got to do what we can, whatever we can, to reduce the maintenance requirement as our customers have said. A lot of that is done through the PLC type control systems so that we can predict rather than rely on demand maintenance. We can predict those things and make sure that we don't take that boiler down at the wrong time, which would be so costly to the process. The other thing is we've gotten rid of a lot of this old refractory. We've replaced it with membraned walls. So now you have a membrane wall, insulation, and an outer casing right here, and that's it. These boilers would require a seal welded inner casing because most of these have a tangent wall. Good boilers. But again, when we're looking at maintenance, this fully membraned type of drum boiler is so much more effective. The only refractory that we're seeing in these boilers is a bit of a seal that you see here, and that's about it as far as the furnace is concerned, and nothing on the front wall either. If we've got the proper boiler burner package, we can eliminate all the throat tile that we used to have, which was used to aid combustion and also help shape the flame. But it's a maintenance headache. And so we as an industry are trying to get away from as much of that as we possibly can. As far as the industries that we're addressing with these boilers, it runs the gamut. And I don't have to read all of these off, but you can see. And this is only a few of what we address. It's mind-boggling where steam is used in this country. I've highlighted the oil sands recovery area as another major market niche, if you will, for our industry. We're doing a lot of good work in the oil sands today, extracting that oil from the sands down deep in the earth. But it's a whole separate topic, and that's why I've got it highlighted in red here. So when you take a look in the final analysis, when checking over the list of demands our customers have been asking this industry to satisfy when it comes to larger water tube boilers, we have, I believe, addressed them very well. And as far as single source responsibility is concerned, that's an evaluation decision amongst the various manufacturers out there. It also ties closely to the high value to cost demand, which is the cost of the equipment. So in other words, what I'm saying here is if you take a look at the single source responsibility and that high value to cost relationship, those have a pretty close tie. And so therefore, in the end, all the criteria, of course, are important and should be evaluated very closely. But we as manufacturers also have to be evaluated in terms of what we bring to the party before, during, and after a sale, if you will. Very, very important that we look at that, because there's more to it. It's a huge capital investment, but it's more than just that initial cost. It's what do we as manufacturers bring to the party to satisfy your need. And so therefore we have to be very acute and tied into this, because we're talking projects that are very expensive and can be very complicated. So, questions?